Flack math! Give me some math and I'll give you some flack. Flack math!
Fast,
so this will be easy. This will be an easy lesson, okay? Even for you. So we're going to talk about fractional exponents. Now, remember when I said negative exponents have nothing to do with whether something's positive or negative? Guess what? Fractional exponents have nothing to do with fractions, okay?
Yes.
It's just the top number is the power and the bottom number is the root. It's that simple, okay? So basically, if I had a to the m over n, this would be the nth root of a to the m, okay? And it doesn't matter what order you do it in. You could do it like that, or you could say the nth root of a all to the m. It doesn't matter, okay?
Wait, so are you simplifying a to the m over?
Yeah, so you could, so the easiest thing to do, like, let me just start with an example. I can't see anything. So let's try this. 3, or let's try 9 to the 3 halves. Okay? So now eventually you'll be able to tell me that this is just 27. Okay? But you have to do the math first. You have to find the second root or the square root of 9 and then cube it. What's the square root of 9?
The square root?
3. And then now cube 3, 27. So this is the square root, or if it's a square root, remember you don't really need a 2 there. And then you got the 9, and then you got the 3. So now you can do this in any order you want. You could find the square root of 729, right? Because 9 to the 3rd power is 729. And then you can take the square root of that, that's 27. Which one's easier? Finding the square root of 729 or finding the cube of 3? Yeah, so when you can, this is kind of like when you're multiplying fractions, when you can cross reduce. So it's easier to divide first before you multiply. Same thing here, it's easier to root first before you power up, okay? So that's what fractional exponents are. Pretty stinking easy. Now, the easiest ones are like, I'm definitely going to need my glasses because I can't see squat. If I just wanted to give you an example, here's example 1a, 3 to the 1/5. Well, the directions will say write with a radical. So how would I write this with a radical?
5 on the outside. And then that, and then the 3.
Yeah, and I don't really need a 1, right?
No.
So that if there's ever just a 1, this is just a root problem. So tell me this as fast as you can. 9. So it's just the square root, because you can ignore that top number. You're not doing a power. So if it's just a 1, you don't have to do a power. It's just the square root of 81. Okay? So nothing to do with fractions, right? And I know how much we all love fractions. So this is nice. We don't have to deal with fractions. Now, fractions, obviously there's going to have to be some kind of fractional math in this, because what happens when you multiply two exponential expressions? You add the exponents, right? Well, if you have fractional exponents, you have to add fractions, okay? But you guys know how to add fractions. So let's try another example. Let's try, we'll just do a little bit of review. The properties, remember when we had, when you have like the square root of 50. Remember, you can break that up into two squares, right? Or square roots. You could say square root of 25 times the square root of 2. So 5 times the square root of 2, whatever, right? That's reducing that radical. Well, the same works for any kind of root. So if I had the nth root of AB, you could break this up into the nth root of A times the nth root of B. Right, girls?
Yes.
Yep. So that's the same thing. Just substitute 2 for N and 25 and 2 for A and B. It's the same thing. So if it works with square roots, it's going to work with any root. Okay, so you can technically simplify a cubed root radical, a fourth root radical, and so on. Okay? So here's what I want to do. I want to simplify, here's example 2a, simplify these radicals. Fifth root of 243x to the 10th. Okay? So with square roots, we were looking for squares inside of the radical, right? So now we're not looking for squares. We're looking for fifth powers. All right? Now there's only a couple fifth powers that are even underneath 243, let alone go into 243.
Does that say 5?
That's a 5. Yep. So fifth powers. So what's 2 to the 5th? 2 times 2 times 2 times 2 times 2. What is that?
2 to the 5th? 2 times 2. 8, 16.
Not 64.
Wait, hold up. I got my calculator.
What's 16 times
Shut up.
What is that?
No, you're not squaring 16. You're multiplying by 2. So 2 times 2 is 4 times 2 is 8.
32?
8 times 2
32.
is 4.
I love calculators.
Oh, 32. I knew that.
Okay, so you're multiplying 2 5 times.
You're making fun of me, but you're
So
not.
if I were to list, like these are my perfect squares, I could list my perfect cubes, perfect fourth powers, perfect fifth powers. But I'm 2, so 32 isn't going to go into an odd number, right? So 32 is not in there. Hey, do not return evil with evil.
He said that.
Did they hit the curtain or something?
No, I just did that on purpose.
Oh, so you're the evil.
Yeah.
There's no class.
All right.
Actually, it's not true. I was cleansed on Sunday.
Here, I'm called for.
Shit.
Random acts of evil. That's good for our culture right now. So 32 doesn't go in there, but let's try 3. What's 3 to the 5th power? Let's see. That would be 3 to the 4th is 81. So 81 times 3. Hey, 243. So this is actually a 5th power. Okay? So we can write it like this. We can separate it. You know how we do it like this sometimes? So this is like the 5th root of 243. Now what about, is there a 5th power inside of there that you can divide out? Yeah, that actually is a 5th power. Okay? So this is actually x to the 10th is a 5th power. Okay? Now, there's not going to be any ones left. You can actually take the 5th root of this. Now, here's how you could do it. You could, well, you already know the 5th root of this is just 3, but then this is x to the 10 over 5. What's 10 divided by 5? 2. So this is 3x squared. Okay? So when you're finding the 5th root of a variable with an exponent, all you have to do is divide these two numbers.
What was the purpose of making the triangle?
Well, that's where we're going to simplify. So sometimes when you simplify like this, you're left with the radical. So we kind of did that with the radical 25, but there is no non-perfect squares in this. Well, there's no non-perfect 5th powers.
Okay.
So we didn't have to do the right side. So this was all simplified to this nice little expression. Okay?
Okay.
You can always check your work by taking this to the 5th power. Okay, so you can check it by saying, okay, let's make sure that this is going to equal 243x to the 10th. So take it all to the 5th power. And what do you do with those exponents again? multiply, and then this is 3 to the 5th, so that's 243 x to the 10th. Yep, it works. Okay. So let's do another example. So it was cold in here, and somebody cranked the heat and made the classic mistake of, oh, it's cold, let's turn it up to 100. That's not how thermostats work. Okay, let's see here. I think that's a 3. Maybe it's a 5. No. Yeah, it's a 5. I just don't like wearing my glasses with a mask because it fogs up everything. Okay, let's simplify this. So this doesn't matter. It's just the 5th root of the top over the 5th root of the bottom, right? So we could rewrite it like this to make it easier. 5th root of x to the 5th all over 2 5th root of 2. Okay? So can we simplify any of that?
Yes.
Yeah. Well, what's the top? What's the 5th root of x to the 5th? That's just x. So your solution is just x over 5th root of 2, or 2 to the 1/5.
Mr. Flack, your 5s look like a T.
Your t's look like a 5.
Well, the other one looks like a B.
Shivery timbers.
Oh, I know that, like, continuing.
What'd you say?
Yeah.
Yeah.
Well,
Yeah,
that-
I'm sorry.
example too.
But you kind of get the idea. So now what's the problem with this? You can't have a radical in the bottom, so what do you do to get rid of it?
No, I don't know.
Yeah.
Well, it's you can't just multiply by another 5th root of 2. How do you cancel a 5th root?
How do you cancel? You add a 5th root to the. No.
No, you have to do this.
I'm
Watch
gonna
this.
stop talking now.
No, you can talk. I like hearing you talk. So you have to
No.
basically do this 5 times. Well, now there's 5. So if you do that to the 5th power, that cancels the 5. So how do you do that to the 5th power? You multiply it together 5 times. So that's what happens up here. So this is basically the 5th root of 2 all to the 4th power. Okay? And then you're just left with 2 on the bottom, right? So this is, let's see, 5th root of 2. So this would be x, or 2 to the 4/5 x all over 2.
Wait, how did you get this to? What?
And you don't have to write it like this. You could just leave it like this. So how did I get the 2 on the bottom?
No, how did you get the answer?
Well, do you see how I just got the 2 on the bottom?
No.
Because I had to cancel this 5th root radical. The only way to cancel a 5th root radical is to raise it to the 5th power.
So you only got rid of the 5, right?
So, yeah, I mean, well, the radical, yeah. So when you raise this to the 5th power, you're basically multiplying it together 5 times.
Okay, so that got rid of the 5.
So that makes this, I'm only multiplying this top by 4 times. So this is, see how this is the same thing as this. I just used an exponent.
Like, how do you
Okay.
get the 2 to the 4/3 x over 2?
Oh, that's a 4/5, but because it's the 5th radical. So I just use fractional exponents to write the answer. I think the book just has it like this. So don't worry about this. You can just write it like this. X, or 2 to the 5th root of 2 all to the 4th x all over 2. So that's how the book has the answer.
Okay.
Okay? All right. And here's what the book went on to do, just because it thinks it's cool. is really 1 over 2. This is just 2 to the 1/2, or 2 to the negative 1. I saw that. Unfortunately. Okay, keep your hands to yourself, but not in that way. Okay, so 2 to the negative 1. All right, so do you see how this is 2 to the negative 1? If I put that on top, it would be 2 to the negative 1. So then I'd have 2 to the 4/5 times 2 to the negative 1, x. And what do you do with those exponents? You add them. So then you just be left with 2 to the negative 1/5 x, which is crazy. Okay. So I don't think you need to do it this way yet, so don't worry about that. But that's just what the book says. Okay. So let's go over some properties real quick to make sure you got it all figured out. All right, so here's properties of rational expressions or rational exponents. So this is just a nice little review of all the rules so far, okay? So a to the negative n equals 1 over a to the n. You guys remember that? If it's a negative exponent, you just throw it on the bottom. Or if it's a negative exponent on the bottom, you throw it on the top. So far, so good? Okay, 0 exponent. A to the 0 equals, what does a to the 0 equal? 1. Anything to the 0 power is just 1. Okay, so Avery to the 0 power is 1. Okay. What about this? A to the m times a to the n. What's that? A to the,
Mn.
not mn,
M plus.
right? You add the exponents. Now, Gracie, what's that? A to the, I called you mn. So when it's a power raised to another power, you multiply. But when it's a power times another power of that same base, then you add the exponents, okay? So this is negative exponent. This is the 0 exponent. This is the product property of exponents. This is the power product of exponents, okay? So, and then we've got, let's see, what else? Oh, the power of product property. So if you have A, B, all to the m, this is just, you just kind of distribute that exponent. Remember that? A to the m, B to the m. So this is also on page 59 of your textbook. So if it's easier for you to copy it down, this is a nice little cheat sheet for you to have. So you're just distributing that exponent to everything inside the parentheses, whether it's a fraction or a whole number, it's at the top and the bottom. Okay, so these are some good rules. That's on page 59. Okay, so now we're going to simplify some expressions here. So this is example 3a, and I want you to give me a simplified version of this. Tried to use willpower to be able to see. This doesn't work. put it over my mask.
That's what I do.
You wear glasses?
Yeah. There's like stuff you can put on your glasses to make them anti-fog.
Really?
Yeah, it's like a spray.
Well, that's good to know. All right, so before you worry about the fractional exponents, you can apply some other rule here. So what do you do with the exponents?
Add them.
Add them, right?
How are we? Okay.
So this would be 64 to the 8/16,
Just 1/2, right?
which simplifies to 64 to the 1/2. What does 1/2 exponent mean? Square root. So this equals 8. That's nice. It started very daunting, but it wasn't too bad. 6/4 over 7/4. Okay, here's 3b. Oh, we forgot one of the rules, didn't we? After the product rule, we have the quotient rule. So a to the m over a to the n is just a to the what? Subtract, right? M minus n. So what do you do with those exponents? Yeah, you could bring this up and make it negative and add them, or you could subtract the exponents. What's 6/4 minus 7/4?
1 negative.
Negative 1/4?
Yeah.
Okay, well, so what do you do with negative exponents?
Put it over 1. Under 1. Over 1. I don't know.
What do you do with negative exponents, not negative?
Oh. Yeah, that's what it says. So,
Yeah, put it under 1. Yeah, put the whole thing. So put it on the bottom. So 1 over 64 to the 1/4. Now what do you do with fractional exponents?
It's the square, or the fourth.
Fourth root, which is, what is that? Just
2, right? Wait, no.
4.
That's wrong.
so 4. That's the cubed root of 64.
6 times 4 is 64.
So unfortunately, this is not a nice little simple answer. So you're just going to be left with it would have helped if I wrote the problem right. So this is 16. It's not going to change much. But now we can take the fourth root of 16. What's the fourth root of 16? 2. So your answer is 1/2.
Oh.
Fourth root of 16. So 2 times 2 times 2 times 2.
Where's the 2 come from?
Because the fourth root is what number multiplied by itself 4 times equals 16. 2 times 2 times 2 times 2 is 16. Okay.
Okay.
All right. I know exponents are hard to think about at 9:30 in the morning. Okay. Let's try another one. Let's try 3C here. 3C is 12 to the 10th all to the 1/5. So 12 to the 10th all to the 1/5. Okay, what do you do with those exponents? So there's kind of like an order of operations of exponents. Exponents is one of the orders of operations, right? Please excuse. But there's an order of operations sometimes with these exponents, but sometimes it doesn't matter what order you do it in. Like I could have put this on the bottom first, or I could have taken the fourth root and then still have a negative number and then put it on, I don't know. But, so what do you do first?
You multiply them.
Multiply. Remember, when you have a power raised to a power, you multiply them. So that's what, 2?
Yeah.
10 times 1/5 is just 12 squared, which is 144. You're done. One more. 3D, 27 times 125, all to the 1/3. Now you could multiply this out if you wanted to, or you could apply this property, which basically distributes the exponent to every factor inside. So you could multiply 27 times 125. That's fine. And then good luck trying to figure out the cubed root. Well, you could just put it in your calculator. You could just do that in your calculator and you'd be done.
Yeah.
But I'm going to distribute this 1/3. This is 27 to the 1/3 times 125 to the 1/3, which is 3 times 5, which is 15. Okay, that's nice. That worked out. That was a nice little shortcut. If I wasn't teaching this lesson, then I'd probably just multiply all of that and then take the cubed root like a moron. But I'm not a moron because I'd still get it right. I'm just making more work for myself. Okay, so now let's get down to the algebra part of it and solve some equations with fractional exponents.
Yeah.
So if you guys remember how to solve for an x squared, what do you do to both sides to get rid of that x squared? You do the opposite of squaring something, which is square rooting. So if you have like a cubic equation, so you have x cubed equals 27, how do you find x? You cube root it. Or if it's the square root of x is 3, how do you solve for x? Well, you do the opposite of square rooting, which is squaring. Okay? So let's try this. X to the 1/3 equals 6. How do you get x by itself?
You take the 1/3 root of it. Right? Or no, you
Well,
cube it.
technically, you could take the 1/3 root because the 1/3 root is cubing it. Okay? So really, we just need to make this an x to the 1. What do you multiply by 1/3 to make it a 1?
3.
Yeah, you just cube it. Okay, so we need to cube it. So we need to multiply, we need to take this to the 3rd power. A better way to think about it, I mean, I guess you could, as long as you could rewrite it like this first. And then finding the opposite operation of this looks a little easier. To get rid of a cube, you cube root, you cube it. So x equals, what is that? 216. Okay. Let's do another one. Here's B, example 4B. X to the 4/5 equals 16. See if you can figure that out yourself. So how do you get x by itself?
Can you give me the first step?
Well, yeah, the hint is how do you make that x an x to the 1st power? Because that's x by itself is x to the 1st power. So how do you turn that 4/5 into a 1?
I'll just.
Quitter?
Yeah.
Yeah. That was a question. That wasn't an accusation. I said, are you a
I
quitter?
said yes.
Any idea? Is it too confusing?
5th root of 16.
Go to sleep.
Did I write it down wrong? No, we're not wanting to find the 5th root. We're wanting to find the 4th root, right? Because look, how do you make this a 1? What exponent do you have to apply to that to turn it into a 1?
5/4.
5/4.
Oh, because you multiply.
So you do that to both sides. You raise both sides to the 5/4.
Yeah.
Okay? So then that cancels, blip, blip, and you get x equals the 4th root of 16 to the 5th. Let's find the 4th root first. What's the 4th root of 16, Gmo?
2.
2. So 2 to the 5th equals
Yeah.
32. That was cool. That worked.
I'm not good at math. Shut up.
All right, I'm going to do one more. First person to get it gets a free problem set.
Okay. now
But if you get it at all, I'm going to give you a free problem set coupon. So remember, you collect 5 and you get a free problem set. So here's 4C. Ready? X to the 4/3 equals 7.
Well, this isn't going to be a nice number, is it?
No,
No.
it's not going to be nice, but you can write it as a radical or you can write it as a fractional exponent. I'm good with either one.
And that is the wrong answer.
So if you get it, you can raise your hand and I'll come see.
I feel like that's wrong. I have to write it down.
Oh, Silas
I
has
have
been
a
waiting.
number, but I think it's wrong. Oh, wait, hold on.
Hey, I missed you, Silas. Sorry. I don't know how long you've been waiting, but make sure you look at the video later. Sorry.
Okay, I'll look at the video. Thank you for letting me in.
Okay. Sorry, just noticed you. If you were here, I would notice you a lot easier.
I have a number, Mr. Flack, but I don't think
But-
it's right.
All right, let's see what you got.
Same here?
I don't know if it's right.
All right, so don't give me a decimal. So
What's
give me
25
a
then?
simplified radical, but you can't really simplify
okay.
the radical.
I mean, that's kind of it. I just have
Well, then
to
how would
use
you?
my calculator.
Yeah, what number is that? Okay,
That's 3.
so yeah, so now you just have to simplify the
Yeah,
inside.
I can't do that in my
I got
head.
I only got
Stop.
that's done.
So that's right.
Is that right? Or is
Well,
it the other way around?
Okay.
Is
So
it-
that you wrote this backwards.
Is it the 3
Yeah,
on the inside?
3 on the inside, 4 on the outside.
Mr.
So
Flack,
but it's
Right,
the
inside the,
4 through.
I'm just saying,
Okay,
replace that
I'm
there.
stuck.
that's it.
Wait, actually?
When did you? Whoa, when did you
wait
get
a
that?
second. hold on.
Like 2 minutes ago?
Really?
Yeah.
All right, I'm gonna give you both a free problem set.
I give up.
Then Gmail, if you get it, I'll still give you.
But like I know
coupon.
how to set it up.
What about,
'cause
wait,
it
you
was
have to,
to that, right?
The 4th power.
Yeah, and then you would take that times the 3 times, whatever that's called,
But it'd be the opposite. It'd be
or 4 times.
that to the 3rd power.
Third power. That's what I said.
Okay, so how do you turn that? Would you get, or did you already
Is it 343 to the
4th root of?
4th root
Yep.
of 343?
Okay, so how do I change that into a 1?
3/4.
All to the 3/4, so that's what I'm gonna do to the 7.
Yeah.
Okay, so that makes it an X, and then this makes it the 4th root of 7 to the 3rd. Well, the only thing, you can't take the 4th root of 7, but the only thing you can do is take the 3rd power of 7, which is 7 times 7 times 7, which is 343. So your final answer is this. That'll work. Okay, good. All right, let's move on. Silas, did you get that?
Yes, I did.
I don't know what we're doing since.
I really
just
don't
joined, I'm
actually.
sorry.
I can just watch the video.
Okay, all right.
Yeah, but I'll just stick around for the end.
Okay,
Just
we've
because.
got one more lesson. I promise I won't ignore.
Awesome.
Okay, so I'm giving Drew and Avery a free problem set.
I told you thought it was sophomore yesterday. You're a sophomore, right? Yeah.
And then
Spanish one like that was last year.
I'm gonna give Gmo and Delaney coupon.
Why are they coupon?
So if you go, now you have 102 points. So if you get 3 more, you get a free problem set. And I'm gonna do more of this stuff anyway. So you'll have more opportunities to get more coupons.
I don't like school.
All right, so if you're still struggling with this, make sure you rewatch this video. But if you need more help, let's figure it out. You can see me at lunch or do a Zoom call. But see how they have nothing to do with fractions, which is kind of nice. The only time we had to do fractions was pretty easy fractions, like adding fractions or multiplying fractions. But then when it came down to simplifying, then they're not fractions anymore. They're just two-part problems. The top is the power, the bottom is the root. That's it. Okay, moving on to lesson 60. All right, lesson 60 is distinguishing between mutually exclusive and independent events. Okay, now we started talking about this with probability. Mutually exclusive versus independent events. Now remember, independent events don't affect each other. So flipping a coin flipping a heads on a coin doesn't affect what your next flip is going to be. It's not going to say the coin doesn't get tired of landing on its face, right? So it's an independent event. Yes.
Can I go to the bathroom?
Uh-huh.
No.
Gross.
Okay. So what's mutually exclusive? So let's look at that. So a compound event is exactly what it sounds like. You're taking two events and putting them together. Like flipping, what's the probability of getting a heads 3 times in a row? That's a compound event because it's 3 independent events happening. Okay? So events that have at least one outcome in common are inclusive events. Disjoint events are events that have no outcomes in common. Okay? So, for example, you could say, what's the probability of you rolling an even number or a prime number? Okay, let's see how there's an even number that's a prime number, 2, right? So those are inclusive events, so like they share a common outcome, right? So in the set of prime numbers, there's a 2. In the set of even numbers, there's a 2. So they have a 2 in common. Disjoint events are events that have no outcomes in common. What's the probability of rolling an odd number or an even number? Well, those are all disjointed. There's no numbers in common. Okay, so let's start with an example. Example 1A, here's a little spinny thing. And let's say that there's all these different things here. Got a 1, 3, 2, 1, 2, 3, 5, 6, 8, 4, 8, 9. Okay, and then you got some that are shaded and some that are not. Okay, this is what the example looks like. So when spinning the number wheel to the right, what's the probability, what's the possible outcomes of this? So there's blue and then there's white. Okay, so these are blue and then these are white. So what are the outcomes? So what are the possible outcomes of doing this? So B1, B2, B3. So these are all the possible outcomes. B1, B2, B3. So blue 1, blue 2, blue 3. And then blue 5, blue 6, and blue 8. And then you've got the white ones, which are W1, W3, W2. Oh, no. W2, W3, and then W4, W8, and W9. So these are all the possible outcomes of this spinner thing, okay? Determine whether the compound events described are disjoint events or inclusive events. Okay, is this disjointed or inclusive? the spinner landing on a blue sector and the spinner landing on a 4. Are those disjointed events or are they inclusive?
Disjointed.
Yes, because there's no blue 4s, right?
Yeah.
So they're disjointed, okay? What about B? The spinner landing on a blue sector and the spinner landing on a 3, disjointed or inclusive?
Inclusive.
Right, because there is a 3 blue. So those are, you might get a 3 in both scenarios, okay? You guys understand the difference? All right, now here's how you calculate the probability of inclusive events. So if you got, and this is just for inclusive events. Inclusive probability is what we'll call it. Probability. Okay, so probability of A or B happening equals probability of A plus probability of B minus that one they have in common. So P of A plus P of B. I'm going to rewrite this so you can see it. So probability of A or B equals probability of A plus the probability of B minus the probability of A and B. Okay? So let me just start with that example. What is the probability of rolling a die and getting an even or prime number? Well, I'm just going to replace even for A and prime for B. Okay? So probability of even plus the probability of prime minus the probability of an even prime number. Okay, so on a dice, on one die, number cube, what's the probability of getting an even number?
3, 1,
3 out of 6, right?
6, yeah.
So 1/2. And how many prime numbers are there in between 1 and 6 inclusive?
2.
2, 3, and 5. So 3, so that's 1/2. Right?
Yeah.
So,
I didn't know 2 was a prime number.
Yeah, I can't get any smaller.
yeah, because there's only 2 factors, 1 in itself.
It'll be just 1. It doesn't count.
Yeah.
Okay, so what's the probability of getting an even prime number? Well, there's only one even prime number, so it's 1 out of 6, right? So your probability is 5 out of 6, which kind of makes sense, because if you think about all the numbers that are either even or prime, it's 2, 3, 4, 5, and 6. So you're only missing 1. So it's 5 possibilities out of the 1. Now, if I said even or prime, I probably didn't have to go through all this crazy, confusing formula. I could have just listed all the numbers that are either even or prime, and there's 5 out of the 6. Okay, but do you see how it makes sense? So the probability of those are going to be added together, but you want to eliminate the one that they have in common because you don't want to count it twice. You counted it twice when you included it there. So you want to just get rid of that one. Only the one that you counted twice, though. Okay, now, obviously for disjointed events, it's just A plus B. Okay, so in a disjointed events, probability of A or B, and this is already, if you know that they're disjointed, equals probability of A plus probability of B. That's it. So if I said even or odd, what's the probability that you're going to get an even or odd number when you roll a dice? What's the probability?
Oh, 5. Probability that you get even or odd.
Even or odd?
Oh, 1, 1.
1, right. So if you just ignore the formula for a second,
Yeah.
well, those are the only things that you can get, even or odd. So what's the probability? You're always going to get either even or odd. Now the probability that you get even and odd is 0. But even or odd, so that's 3 out of 6 plus 3 out of 6, which is 1. Okay? So the formula is helpful sometimes, but if it's like rolling a dice, you can count those out in your head, how many different possibilities there are. Okay, now the disjointed events, and sorry, basically we call these mutually exclusive. So instead of disjointed, we're going to call them mutually exclusive. So that's where that word comes in. And it kind of makes sense because it's the opposite of inclusive. Okay? So inclusive means they share some solutions or possibilities. But mutually exclusive means they have no outcomes in common. Okay. Does this make a little more sense?
Yeah.
So basically probability, you have to consider probabilities that share the same outcomes. So that spinning wheel just stresses me out. So let's move on to a different kind of example. All right, so here's example 2. Find the probability. So here's the deal. Jar contains 10 marbles. 10 marbles. All right, we can do this. 10 marbles, 5 are red, 5 red, 4 are blue. We got 1 more left, right? So 1 is green. Okay? The red marbles are numbered 1 through 5. So these are numbered 1 through 5. Okay, so you've got a red marble with a 1 on it. You got a red marble with a 2 on it. You got a red marble with a 3 on it. You got a red marble with a 4 on it. You got a red marble with a 5 on it. Okay, the blues are numbered 6 through 9, and the green one has a 10 on it. Okay? So far, so good? You understand what the jar looks like? Okay? It looks like Spider-Man and then the spider that bit him, maybe. I don't know. Like red and blue, and then there's one little green thing in there. I don't know. I can imagine it's very colorful, very marbly. All right, so here's example 2A. What is the probability that you're going to get is blue or even? Probability of blue or even. Okay, now does blue or even share any outcomes? Are there any blue even numbers? Okay.
Yes, shall.
Right, so remember the blue marbles are labeled 6, 7, 8, and 9. So 6 and 8 blue, those are the ones that we have to eliminate. So remember, this is going to be P of blue plus P of even minus P of blue even, or even blue. Okay, so you have to determine whether this is mutually exclusive or inclusive. So if they share anything, if there is such a thing as a blue even number, then it's inclusive. So you go this formula. If there's not, then you can just add the 2 probabilities. So let's add the 2 probabilities. What's the probability of getting a blue?
4 and 10.
4 out of 10. And then even?
5 and 10.
2, 4, 6, 8. Yeah. So, and 10. So 5 out of 10. And then what do they have? How many do they have in common? They have 2 out of the 10, right? So you don't have to reduce it. If you reduce it, it's going to be a more difficult problem.
Okay.
So just leave it like that. 4 plus 5 is 9 minus 2 is 7/10 probability. Okay? You guys good with that?
Yes.
All right, I'm not going to do the next example because it's easy. You just add the two probabilities because it's going to be mutually exclusive. What's the probability that the marble is red or has a 2-digit number? Can you do that in your head? 6/10, right. So it's red is 5 out of 10. The only 2-digit number is 10. So that's just 5/10 plus 1/10, which is 6/10, 3/5. Good. Okay. Now, and then you can kind of combine this with your dependent and independent events. Remember dependent and independent events? Dependent and independent events, like a coin that is flipped is independent because it doesn't affect the next one. Okay, so let's do this. Here's example 4. Here's what it says. Ready? This is my last example, and then I'll be done. Okay. 2 fair coin tosses are flipped 3 times. You flip a coin 3 times. Okay. So you flip 2 coins 3 times. Okay. Find the probability that both coins come up heads and 1 tails all 3 times. Okay. So heads and then 1 tails all 3 times. So 2 heads and a tail. So I want to know what this is. Probability of heads, heads, tails. Okay. Since each flip does not affect the next one, the events are independent. The formula is you're just multiplying. Okay. So you've got this happening, which is probability of heads times the probability of heads times the probability of tails, right? Okay. Now, so that's just 1/8, right? 1/8 times 1/8 times 1/8. So why? Yeah. So why did I say 2 fair coins are flipped? That's silly. Okay. All right. And then example 3, since the bell's going to ring in like a few minutes, let's look at example 3 again. This will probably be a different, better scenario than the coin toss. This is stuff you did in Algebra 1. Example 3 looks like this. You got 9 white marbles, 7 green marbles. Determine whether the listed events are dependent or independent. Okay, we've done this. So you got 9 white marbles, 7 green marbles. You ready? Can you see the jar? 9 white marbles, 7 green marbles. A white marble is selected and replaced. Then a green marble is selected. What's the probability of that happening? So 9 white, probability of white, then green. So remember there's 9 white. And how many are green? 7 green. So what's the probability of a white marble being selected, then replaced, and then a green marble being selected? Well, you just multiply them together, right? Because they're independent events. What's the probability of drawing a white marble?
9 out of 16.
9 out of 16. Do you see where I got 16?
Yes.
Because total marbles. Times 7 out of 16, right? Because you're replacing the marble. So after you take it out, you put it back in. Now there's still 16 left in there. All right. So what if I did the same scenario, but didn't replace it? So what would it be? So this is with replacement. Without replacement looks different.
It would be 9/16 times 7/15, right?
Yep. So it'd be 9/16, and there's still 7 green marbles in there, but there's 1 less total marble. Okay. then you're stuck with that. So still 63, but then you've got one less of those. So what is that, 240? Okay, that's it. This is more review. You guys did that in Algebra 1. But that's all I got. Good job.